quark color hypothesis. In the very beginning of the knowing about the quarks, only three quarks, that is down quark, up quark and strange quarks are invented, were discovered. But later on, the quarks have been increased to 6. They are down quark, up quark, strange quark, charm, top and bottom. These are the 6 quarks that are presently known. As the quarks that are present in the neutron are violating the exclusion principle. Thus, this violation of exclusion principle can be explained by the quark color hypothesis. Let us consider, for example, the electric charge is divided into 2 types, that is positive and negative charge. When this positive charge and negative charge are combined together, then there will be the formation of neutral hole. In the same way, the quarks, in the term of quarks, this color property, that is the color property, can be manifest. How the quarks are having the same quarks in the same particles. In terms of quarks, this color property that can manifest in 6 different ways, that is red, blue, green, anti-red, anti-blue and anti-green. This is the quantum property that can be used to distinguish the quarks from one another. This color property, quark color hypothesis, can help us in understanding how the different colors can come together to create a hadron particle. In classical, the analogy is that when we talk about the primary colors, that is red, blue and green, when they are combined, we get the white color. And similarly, in the quantum mechanics, in the quantum state, the analogy with respect to quarks and the hadron particles is that all hadron particles are colorless. We consider all the hadron particles are colorless. Supposed to be all the hadron particles are supposed to be colorless. So, a baryon particle having the red, blue and green color can result in the hadron particle color. The resultant hadron particle will be the colorless. This property is intrinsic to the nature of quarks only. When the quarks come together and combine, then this property is relevant. But beyond the quarks, this property is irrelevant. Here, the colorless means the absence of color property. This color hypothesis also explains why certain kinds of quarks are not found, such as the quarks having the quarks up quark down quark. Only these two combinations are not allowed. Why? This is explained by the color hypothesis, because the up quark and down quark having, let's suppose, red and green. This red and green color combined to form will not be colorless. Thus the quarks having thus the hadrons of two quarks is not possible, but the hadrons having one quark and an antiquark can be formed, because red and anti-red will be colorless. Thus this is allowed, but the two quarks is not allowed in the hadrons. Having one quark and antiquark is allowed in the formation of the hadrons. But in the recent discoveries, a few days back, recent discoveries, we have found the tetraquarks and pentaquarks. In few days back, the discovery of tetraquarks and pentaquarks has took place. This is officially published in CERN website. They have come to know that the tetraquarks and pentaquarks are formed, but very less time, very less time, they are divided in forming. They are further divided in forming three quarks or one quark and anti-quark. This is recently observed in the CERN laboratory. This leads to the question that there may be different kinds of quarks, not only the tetraquark or pentaquark, but much more quarks that we are not able to experience. We are not able to notify them. The peculiar property of the color is very much intrinsically linked to the idea of strong force itself. Sometimes because the quarks are attracted to each other because of strong force. Thus the strong force is even sometimes called as color force. It turns out today we have come to know that there are tetraquarks and pentaquarks. Thank you, sir, for giving me this opportunity.